Hello guys, welcome back to my channel Gamma Di Gamma. Today I'm going to be doing an electromagnetic induction essentials video. So let's get to it. So electromagnetic induction starts because a guy named Faraday, Michael Faraday, did some experiments. So what he did was he took a coil with multiple turns, if you will, had say like a resistance over here, and then he took a bar magnet and he brought it close to the coil, and interestingly a current was recorded. A current flowed through this circuit. Now that's interesting because Michael Faraday then did some more analysis of this, and then he found out that initially when you weren't moving the bar magnet, there the number of field lines cutting these loops was a constant, was fixed. But then when you move the bar magnet close to the coil, then there was an increase in the number of field lines cutting. So there was a change in field lines. Now that is important. So one first observation is a change in field lines, magnetic field lines. I think that's pretty clear. It's magnetic field lines. So what this coil tried to do was, since there was an increase, it didn't like this increase apparently. So it tried to oppose it. And how did it oppose it? So here's a north. You can oppose a magnet by having a like pole. If you can develop a north polarity on this coil. Now one way to develop a north polarity on a face of a coil is having current go in the anti-clockwise direction. So if a current goes like this, then it will totally oppose it. That's how the current was recorded. That's exactly what the current in the circuit looked like. Okay, and now once the bar magnet was closed, he tried to pull it back. So let me draw the coil once more, connect it to a resistance, and once the bar magnet was closed, after pulling it close, he tried to push it off. So when he pushed it off, the coil didn't like that either, because again there was a change in field lines cutting through the coil. So what the coil tried to do is it tried to attract this north because it didn't want it to go away. So it created a south polarity on its face. One way to do that is to have a clockwise current. So basically you can see now that the current flows in the opposite direction. And now based on these observations, Faraday came up with laws. So the first law, you can say Faraday's first law of electromagnetic induction, or Newman's law simply, gives the direct formula for the induced EMF. So basically this is the induced current because it was induced by the change in magnetic field lines. And when there's an induced current, there has to be an induced electromotive force, an EMF. So the induced EMF, the magnitude of which is given by the rate of change of magnetic flux cutting through the coil. And now you can add a negative sign, but I'll justify this negative sign based on the second law. Now many textbooks also have multiplied the number of turns along with this, but it's up to you because you can totally club this in the magnetic flux formula. So the second law is Lenz's law. Now Lenz's law says that the direction of induced EMF is such that it opposes whatever caused it. Now we can go back to the first law and see that one way to produce an induced EMF is to change the magnetic flux with respect to time. And look at the first example. When the magnetic flux increased, it didn't like it, it tries to oppose the increase. So the current was flowing in the opposite direction. Same with the second example. When there was a decrease in magnetic flux, then current flowed in such a way so as to oppose this change. That's why we have this negative sign, because both of their directions are different. So in essence, electromagnetic induction is all about satisfying the coil, or how a coil satisfies itself by, because it doesn't like an increase in the magnetic flux. And yeah, that's magnetic flux is basically a fancy term for the number of field lines passing through surface. Now, one question you may ask: we know the magnitude, but how to find the direction in more dynamic scenarios? So the direction of the induced EMF you can know by using Fleming's right hand rule. Fleming's right hand rule. So it's basically just like the left hand rule, but in this case you're going to need to flex your right hand. So here's my thumb, here's my index finger, and here's my central finger. So now in this case the thumb is pointing in the motion of the conductor, which is basically how you move say the bar magnet, or it can just be a metal conductor. It depends. I mean, something has to move relative to, it's either the coil that moves or the bar magnet that moves. I put it that way. There should be relative motion between them. So whatever is moving in your frame of reference, the thumb will point in that direction, and then the index finger points in the direction of the magnetic field. Then your central finger will give the direction of induced current or EMF, or whatever. EMF and current will go in the same direction. So this is basically a very useful thing. Now the first derivation that we have, so called, for this part is when you have a metal sheet, if you will, or a metal plate that is moving in a magnetic field, there will be an induced EMF across it. So magnetic field, if you remember my last video, is pointing inwards. It's penetrating the plane of the paper. Let's call this dimension B. This is L, and yeah, this is the direction in which it is moving, velocity. Okay, and if you remember our formula, if you remember Newman's law, it says that you should have a rate of change of magnetic flux. Now ask yourself, is there a rate of change of magnetic flux? If you look closely, there is, because the magnetic field is pointing inwards. If you take an instant in time, this is how much it, say, moved ahead. Well, there is a change in area, right? There is this dA, this small infinitesimal change in area, which I am shading. And I'll write the formula for calculating magnetic flux. It's basically closed integral of B bar dot dA bar, just like your electric flux. So it's B, then dA, and then you can say cos theta, angle between them. So it's basically BA, the total area of that surface, and the cosine of theta. Now you can also add a term for the number of turns, if you have like a coil moving or something like that. So essentially, magnetic flux is given by NBA cos theta. Now a magnetic flux can change when any one of these terms changes. It should be either theta, it should be either area, it should be either the magnetic field or the number of turns. Now the number of turns, is very impractical to change dynamically. Now look at this figure. What is changing? Well, you might say instantly because I wrote it down for you. Is that the area that's changing, right? The dA. So remember what we wanted for, according to Newton's law, we wanted the negative of the rate of change of magnetic flux. So d phi over dt. I have to differentiate this equation. So let's differentiate it now. D phi by dt is equal to, okay, we'll just take a number of turns to be 1 for now. Now what's changing? The area is changing. The magnetic field and theta is not changing, and theta is 180 degrees because the area vector is pointing outwards, the magnetic field is pointing inwards. Theta is 180 degrees, and you have to put, for the cosine of 180, you have to put a negative here. So it's minus b, then area is changing, so dA by dt. Rest everything is constant. I pulled it out. Now area can be written as length times breadth. Now that if you see in this motion, the length remains the same. It's just the breadth changing. Like this new breadth causes more magnetic field line, more or less magnetic field lines to cut through the surface. So minus b, length remains same. Now change in breadth with respect to time, well, that's just your velocity, isn't it? So negative blv. And now by Newton's law, E is equal to minus d phi by dt. We have d phi by dt, we just multiply another negative and we have blv. That's the magnitude of the induced EMF. Now what's the direction? Okay, let's use our Fleming's right hand rule for that. So the motion, so our thumb is going this way now, the motion of the conductor, and the magnetic field is pointing inwards. Index finger is, say, going like this, and then your central finger will be across like this. So along the length of the conductor. So you have basically current going this way, the direction of your induced current going this way. So if you can attach a voltmeter to these ends of this end and this end of the metal sheet, will actually record a potential difference as the metal sheet is moving through the magnetic field, and its magnitude will be given by this blv. So, and this is a very important formula. It's good if you memorize it. It will be required for many more numericals. Now the next we have is for a metal sheet that's rotating about an axis. So you have say a metal sheet like this, and it's fixed about this point. It's rotating about this point naturally. So first ask yourself, is there, okay, magnetic field is pointing inward here before anything else. Before, ask yourself, is there any change in magnetic flux? Now the magnetic flux formula is given as NBA cos theta. Cos theta is -1, so negative NBA. Now is there a change in any of these quantities? Magnetic field, no, we assume it to be uniform. Number of turns we'll just assume to be 1 for now. It's just one metal sheet. Now area, well, yes, it is changing. How is it changing? So when see this thing rotates by a small amount, call this small amount d theta, this small angle d theta, this rotation, small infinitesimal rotation. Well, then there is this change in area, right? And because of this change in area, more or less field lines will be cutting through the metal surface, uh, per second. So we can find this small dA. We can create a formula for the small dA. Let me just draw the small dA over here. So d theta, the entire thing has an area of dA. Okay, now looking at this almost looks like a small triangle, right? This has the radius, you can say the length of the rod. The radius is the length of the rod, and you can say basically that the arc length, this arc length is radius times the angle, so LD theta. Now to find the area, first know that this curvature is so small that it is almost flat. It's almost like the base of a triangle. So you can just find the area, dA of this thing, by assuming it to be a small triangle. So area of a triangle is half into base. Now the base is LD theta into height. Well, the height remains L and LD theta. So L squared times d theta. Now we can find an expression for d phi over dt. Well, the magnetic field is a constant, dA by dt. We can differentiate this with respect to time. So dA by dt, well, the length is a constant, L squared by 2, d theta by dt. Now if you know your rotational motion well, you know d theta by dt, the rate of change of angle per unit time is omega, angular frequency. Omega L squared all over 2. Well, you can just substitute that over here. So minus b omega L squared by 2, and let me create like a partition. Well, by Newton's law we know that E is equal to minus d phi over dt. You get rid of the negative sign. All you're left with is half b omega L squared, and you know that velocity is equal to L omega. It's all rotational motion now. Then you totally have the formula half BLV. That's the magnitude of the induced EMF. Now for the direction, you can just use the Fleming's right hand rule, and I'll probably leave that as an exercise to you guys. So now let's move to what's called self-induction. So what you do is you again use a coil, that say a similar coil that Faraday used, but instead of just having a resistance, you connect it to a DC battery. I repeat, it's a DC battery for now, and again you have the load. And okay, when the battery is disconnected, when the battery is switched off, no current flows, you can say the magnetic field lines, magnetic flux through this thing is zero. But once you turn it on, see, current will flow like this. So the current will have a magnetic field of its own, if you remember the last chapter. So from zero, there will be some magnetic flux through this when see the current is initially traveling to the first loop. And because of Newton's law of there will be an induced EMF, and Lenz's law says that it will oppose the change. So the current increase was in this direction. It will try to kill the increase in current. So this is the direction of your induced current. And that's just for the first loop. And when, say the current reaches the second loop, there will again be an increase, because there will again be an induced current, because second loop did not have any magnetic flux initially, but then when the current reached it, the current produced like a magnetic field through it. So even that will add to the already established induced current in the circuit. Same with the third loop, and this will continue until the time the current regularizes, and all three loops have, say, the uniform amount of current. So like the current reaches back to the circuit, and the supply and the retreat of current is well balanced out. That's when the induced current will stop, because at that point your magnetic flux will have a stable high value, say a high constant value, but it will be stable because even the current stabilized, right? Initially that happened because there was no current going through, and then when you just randomly turned it on, there was an increase in current. So from 0 to something, that increase in the magnetic flux will cause an induced current, until the time that the magnetic flux reaches a final value and stays the same, because then the current just regularizes through the circuit. And this is also true for when now the current is regularized and everything, and then you just randomly turn it off, and you turn the power source off. So from when the current regularizes, the magnetic field will have some high constant value. Okay, and when you just kill the switch, it again suddenly drops back down to 0. So you can see there's a change in magnetic flux in a matter of seconds, and the coil doesn't like that. So what it does, it tries to mimic what the steady regularized current state was. So initially the regularized current had this direction, but when you turn it off, no current flows. But then the coil doesn't like it. It doesn't like the change. It tries to oppose the change by trying to mimic the current that has been turned off. So it mimics it by producing an induced current in that direction. Now one quantity that's really important, or tells you the strength of this coil, which you call an inductor. This coil I've been calling is actually an inductor. Now there is one quantity that can tell us the strength of an inductor. And what's the strength of an inductor? It's its ability to resist the change in magnetic flux. So it's rightly given by phi over I. Magnetic flux, which has units of Weber, and current, which has units of ampere. And this L is called the coefficient of self-induction. It has a unit of Henry, SI units, everything. Now you can just write your magnetic flux as Li, and but we are interested in differentiating it because Newman's law. So d phi over dt, you add a negative sign to do the same over here. Now the coefficient is a constant, so it will be di over dt. But then what's minus d phi over dt? Well, it's just the induced EMF. So this is another formula when you're dealing with self-inductors. It's good to memorize this formula, minus L di by dt. But in this relation, L is a constant. But what does L actually depend on? Well, naturally, it's we can make a substitution for phi as NBA. We're ignoring the cosine now over I. Now the magnetic field of this solenoid, because the inductor or the coil is a solenoid. If you remember, your magnetism is mu naught Ni, and then there's this A over I. This I was already there in the denominator. The currents cancel out. Now what was small n? It was your number density. It was number of turns per unit length. So you can make that substitution back. So 2 number of turns, so n squared mu naught A over n. So that's basically what the coefficient of self-inductance depends on. Then we move on to what's called mutual induction. So for this, you have not one but two inductors. Or for some of you who are not still comfortable with that terminology, I can say coils. You have two coils now. So let me just draw them out for you here. So now when I run current through the first coil, well, the current, we're not interested in what happens, like how the first coil opposes this increase in current. We're not interested in that now. So when the current, say sets up its magnetic field will look something like this. Wish I had drawn bigger coils, but I think you get the idea. Looks something like this. So what will happen is basically this magnetic, you place the coils in such a way that the magnetic field produced by the first will cut through the coils of the second inductor. And now, since from initial magnetic field 0, when there was no current through the first coil, no magnetic field, the magnetic flux was 0. But then because of the first inductor, let's call it primary, the primary inductor, there was a change in magnetic flux in the secondary inductor to some value. So there was this change, right? Some value. There was a change. So now this change will cause a current through flow in an induced current. We set up an induced current in the secondary inductor, so as to oppose the increase. Now you can say that it will try to create its own magnetic field in this direction, and then you can find the direction that the current will flow. So now the direction of current is reversed from what the direction was in the primary. And similar thing happens when after running the current through the primary for a period of time, you directly just kill the switch. Then there's again a change in magnetic flux across the second, because then it had a steady value when the current was running. When you kill the switch, just the change is, there is a change, so because it just drops to 0 from that value. So it will try to mimic the original magnetic field. So because it doesn't want the original magnetic field to just die down, so it will try to have a magnetic field like this, and in that process an induced current will be set up this way, corresponding to the magnetic field that it doesn't want to die. And now we can find, say, what the strength of the second coil with respect to the first. That's called the coefficient of mutual induction. Coefficient of mutual induction. Now the unit remains the same. Unit is Henry again. The formula is the number of turns of the secondary times the magnetic flux through the secondary all over the current through the primary. And you can also convert it into this induced EMF in secondary is negative M times D current through the primary with respect to time. But then what does M depend on? You can make a substitution for phi s. You get mu naught NPNS AS by LP. If you don't understand what I did, you can just make a substitution in the place of phi s is NBA and then substitute for B. You end up here. It's similar to self-induction. Now let's do some questions now. We know the essential formulas. We have a square loop of side 10 centimeter. You can convert it into meter, 0.1 meters, and 100 turns. So n is 100, and see the initial magnetic field that it was placed in a magnetic field of 0.04 Webers per meter squared. You can also write this as Tesla, and it was then taken. Then it was just taken away from the region of magnetic field. So the second magnetic field is 0. You can say the magnetic field was just turned off, and this task was done in 0.05 seconds. The turning off of the magnetic field, it was done in 0.05 seconds. Well, since there was a change in magnetic field, you can guess that there has been a change in magnetic flux. So what was the formula? N A and the change in the magnetic field, because we are writing that directly the change in magnetic flux. N and A are constants. So 100 times 0.1 into 0.1, because this was just the length, times, well, the change from 0.04 minus 0 is 0.04, and this turns out to be 0.04 Webers. You can find the magnitude of the EMF as the rate of change of magnetic flux per unit time. We're finding averages because there's no point in taking derivatives. You just given us the average time. 0.04 over 0.05 is 0.8 volts. Yes, you might have noticed I ignored the negative sign because right now we're not describing any direction. We just want this value of 0.8. Even if it were like negative 0.8, it wouldn't hold much significance now. So answers 0.8 volts. This is EMF, same unit as potential difference, volts, 0.8 volts. Now we have a very interesting question. They already tell us the magnetic flux through a coil is given by this function 4t squared plus 5t plus 12, and look how conveniently it's a function of time. So we can without hesitating we can just differentiate with respect to time, because E is d phi over dt. I'll just skip the differentiation, all the formulas and stuff. Answers 8t plus 5, and they're telling us to find EMF at t equals 3. So we can just substitute t as 3. 8 times 3 plus 5 is, I believe, and yeah, this was micro Webers, so this will be microvolts. Otherwise you can write it as 29 into 10 to the power of negative 3 volts. So this is milliwebers, not micro Webers, milliwebers and millivolts. This is a pretty easy one, and let me remind you, if you know, they tell you to find, say, like the coefficient of mutual induction or something, and they have like a graph of phi versus I, say something like this, and they tell you to find L. You just need to take the slope of this graph, phi versus L graph. Sorry, phi versus I graph. That's, easy as that. Now you have a plane that's flying. Say you have like a random plane that's flying. It has like a velocity v, you can say, and they're telling us that the plane has a velocity of say 300 meters per second, and the vertical component of Earth's magnetic field is 3 into 10 to the power of negative 5 Webers per meter squared. And since the plane is moving in a magnetic field, they're telling us to find the potential difference developed across the wings, and they've given us the length of this wing. So call this entire length L. They've given us a value for L, and that's 30 centimeters. Now you might want to, if you're intrepid and curious, you might actually want to use your right hand rule and check for what direction the current is, and you might know that the current will go like this as the induced current. And we know our formula for that is equal to BLV. Substitute everything in 3 into 10 to the power of negative 5 into 300 into 30. You get an answer of 0.27 volts. And let me remind you that when a plane is moving, it is always the vertical component of Earth's magnetic field that actually seek to produce an induced current or an induced EMF across the wings. Because a horizontal component, well, it won't do any good, right? Because it won't do any good, because you remember your Fleming's right hand rule. The motion and the magnetic field had to be perpendicular to each other. Because if you have BH over here, the motion and the magnetic field is in the same direction, it won't contribute to any induced current. This component won't contribute to any induced currents. Only the vertical component will. So anytime you're given Earth's magnetic field, like the total Earth's magnetic field, and then you're given like an angle, say theta is 60 degrees, always find BV for such problems, which is B sine theta. The second example is they're telling us to find they're telling us that an EMF of 0.5 volts was developed in the secondary coil they're giving us the time interval 300 milliseconds. So 300 into 10 to the power of negative 3.3 seconds. When current changes from, so it's always the primary where the current initially starts. When the current changes from 2.5 amps to 5 amps, so you can calculate the change in current to be 5 minus 2.5, which is again 2.5 amperes. And we know the formula for the EMF developed across the secondary. They're telling us to find coefficient of mutual inductance. So ES is equal to M times delta IP over delta T. Now we can just resubstitute everything. 0.5 is equal to M times 2.5 over 0.3, which implies that M is 0.06 Henry. Yeah, that's your answer. Some problems are like really easy. It's all about substitution. Now, before I end this video, I would like to do a small derivation that it's highly unlikely that they'll ask, but it's useful when you're trying to build up on another chapter. So you have like a coil and you have a magnetic field. Okay. And basically you turn it about like say you have like a central axis, you like turn it. Then they're telling us to develop a formula for the magnitude of the EMF, induced EMF. Now ask yourself this: is the magnetic flux through this coil changing? Well, you can connect this to a resistance because some EMF would be developed. So is the magnetic flux through this coil changing? If you say yes, then you might ask yourself what component of this formula is eliciting the change. I mean, what thing is changing in this formula so as to provide a change in magnetic flux? Well, it's not the number of turns, it's not the magnetic field, it's not the area. Well, it's the angle, right? Because what was theta? The angle between the area vector and the magnetic field. The magnetic field is always pointing inwards, but when the coil rotates, this plane, it will keep on rotating and the angle theta will change. Hope you see that. So like when it's like when the plane of this thing is like perpendicular to the plane of paper, that's when maximum lines will cut, and when it's like this, the same plane as the paper, that's where the minimum field lines will cut. So there is a change because of the angle between the area vector and the magnetic field. So a d phi over dt would only constitute, well, you can just okay, let me differentiate this. NBA d over dt of cosine of theta. Well, you can just differentiate cosine to get a negative NBA sine of theta, and using the chain rule we have a d theta over dt, and then you can d theta over dt then omega NAB sine theta, and that's your d phi b over dt. By Newman's law, we know the negative d phi over dt is the magnitude of the EMF, so the EMF is omega NAB sine theta, and I prefer to write theta as omega t. Now this will stay a constant because it depends only on the nature of the initial coil. It's E naught, call it E naught sine omega t. You can call that the peak value of the EMF, and this is where your AC current starts, because the current, because the EMF, because of this formula, this equation is a sine wave, right, in time, and it has this peak value of E naught, which depends on omega NAB, all the factors of the coil, how fast you're rotating it, the number of turns, the area, and the strength of the magnetic field. That's where your AC current starts. So I hope you like this video. Please like, share and subscribe. Have a great day. If you have any doubts, please comment, and again, have a fantastic day.